This video briefly covers air-fuel ratio and lambda. In an engine, fuel and oxygen are burnt through the process of combustion. Typically, this oxygen comes from the air. The ratio between the mass of air in the engine and the mass of the fuel is known as the air-fuel ratio, or AFR. As AFR is the mass of air divided by the mass of fuel, a higher value would mean more air, or less fuel, and a lower value would mean less air, or more fuel. Often you will hear this described as richer or leaner, where a higher AFR is leaner by adding air or removing fuel, and a lower AFR is richer by adding fuel or removing air. For a given fuel, the theoretical AFR for complete chemical combustion is called the Stoichiometric AFR. For gasoline, like petrol from the pump, this is typically 14.7, but for other fuels it is different, such as for methanol, the Stoichiometric AFR is 6.47. Calculating the stoichiometric ratio is done from the fuel's chemical formula, which we won't cover today. All you need to know is chemically stoichiometric is the exact amount of air needed to burn every single drop of fuel, with no excess air or fuel left over. Too much air, not enough fuel, the mixture is lean, or AFR is greater than stoichiometric. Too much fuel, not enough air, the mixture is rich, or AFR is less than stoichiometric. So for a gasoline with stoichiometric AFR of 14.7, to theoretically cleanly burn 1 kilo of fuel, we'd need 14.7 kilograms of air. For various reasons not covered today, engines can't always operate at stoichiometric AFR. For gasoline engines with a stoichiometric AFR of 14.7, a normal range of operation will be between 12 and 18, with an acceptable range of about 6 to 25. Rather than quoting AFR ratios, a lot of modern tuners and professionals will talk in lambda. Lambda, which is a Greek letter, represents the AFR relative to the stoichiometric AFR. So lambda is the actual AFR divided by the stoichiometric AFR. What this means is that stoichiometric conditions, lambda is 1. For rich conditions, lambda is less than 1, and for lean conditions, lambda is greater than 1. If we go back to the acceptable ranges for gasoline AFR, we can convert the 18 into lambda by dividing by 14.7, which gives a lambda 1.2, and convert our AFR 12 by the same method divided by stoichiometric 14.7 to lambda 0.8. Therefore, the normal range is between 0.8 and 1.2 lambda. The reason lambda is often used rather than AFR is that lambda is impartial to the fuel used. Lambda 1 is always stoichiometric, above lambda 1 is always lean, and below lambda 1 is always rich. Almost all modern cars have an oxygen sensor in the exhaust. Most cars have even more than one sensor. This sensor is often called a lambda sensor, as by measuring the oxygen left in the exhaust, the sensor can report the lambda the engine is running at, without needing to know the fuel the engine is being supplied. The sensor can be converted to display AFR by multiplying the reading by stoichiometric AFR, but this obviously needs to be the correct value for the correct fuel. Before we finish, it is worth noting there is also fuel-air ratio, or FAR, and equivalence ratio. These are pretty similar, but AFR and lambda are simply the inverse. You'll rarely see these used, but in case you do, the formula are simply AFR is equal to 1 over FAR, and equivalence ratio is equal to 1 over lambda. So, in this video we've covered the very basics of AFR and lambda, including the relationship between the two and what it means to be stoichiometric.